Have you ever wondered why some of the universe's biggest discoveries began as mistakes, contradictions, or results no one wanted to believe? Again and again, the cosmos has revealed things that overturned our favorite certainties. Hidden matter outweighing everything we see, energy pushing space apart, signals and structures that refuse to fit our neat equations. Tonight, in the quiet of the galaxy scientist, we'll drift through these cosmic controversies with calm curiosity, letting each idea unfold at its own soft pace. No rush, no pressure, just settle in, breathe slowly, and when you're ready, we'll wander a little deeper into the dark together, unhurried and warm. Have you ever noticed how easily our picture of reality can slip and rearrange itself? For a long, long time, people were sure that Earth sat still in the middle of everything, solid and favored, with the heavens turning politely around us. Then, almost quietly, that picture cracked. Our world became a moving world, circling a star that was only one light among countless others. And that was only the first time the universe asked us to let go of certainty. Gentle ripples in the cosmic background, strange radio murmurs that blink and vanish. Each new surprise has nudged us to rewrite what we thought was unshakable truth. It helps, sometimes, to imagine the people inside these moments. Careful observers bent over worn notebooks, bold minds whispering ideas that could cost them safety, reputation, even freedom. They argued over how the universe began, puzzled over a faraway star that dimmed in ways no simple eclipse could explain. Their stories remind us that the universe is not tidy or tame. It is stranger than we dare to assume, and even our most trusted ideas may one day be set gently aside. For many centuries, the sky felt orderly. From ancient Greece through medieval Europe, the Earth-centered, or geocentric, model was more than a diagram. It was a way of feeling at home in creation. Earth at the center meant humans at the center, watched over, important. Philosophers framed it, theologians blessed it, and ordinary people looked up at the circling stars and felt sure that this was the way things were meant to be. Then, in a quiet corner of Poland, a thoughtful man began to doubt that comforting picture. Nicolaus Copernicus was a mathematician, an astronomer, and a church official. He prayed, he studied, he watched the wandering planets night after night. Over the years, tiny mismatches piled up in his mind. The motions did not quite fit the old scheme unless you twisted the numbers into knots. Slowly, almost reluctantly, he entertained a different thought. Perhaps it was not the sun that moved around us, but we who moved around the sun. In the model he drew, the sun sat in the center, and Earth became a traveler. Our planet spun on its axis and swept in a wide circle, just as the other planets did. The idea sounds simple now, a neat swap of roles, but at the time, it was as if someone had reached up and gently shifted the entire sky. If Earth was not fixed and special, if we were one world among many, what did that say about our place in the story of existence? Copernicus understood the weight of what he was suggesting. The Church taught that Earth, and humankind with it, held a central, God-given position. Sacred texts were read as if they confirmed that special status. To hint otherwise was not just a scientific disagreement. It brushed against the charge of heresy. So he waited, he revised, hesitated, tucked his calculations deeper into his desk. Decade after decade passed like this, his sun-centered universe alive, mostly in his notes and in the small circle of people he trusted. Only near the end of his life did he allow his great work on the revolutions of the celestial spheres to be printed. The story goes that he saw a copy on his deathbed in the year 1543, the ink still fresh, as the world he knew tilted beneath him. At first, the reaction was muted. Some scholars treated his model as a clever mathematical trick, useful for predicting planetary positions, but not to be taken as a description of what was really out there. The great shift he had begun moved slowly, like a distant planet against the stars. Then another figure stepped onto the stage with a piece of glass and a restless curiosity. Galileo Galilei did not invent the telescope, but he refined it, coaxing it to magnify the heavens many times over. When he lifted it to the moon, he did not see a flawless divine crystal. He saw shadows, jagged lines, bright peaks and deep, dark basins. The moon looked rough and scarred, more like a cousin of Earth than a perfect, heavenly jewel. Turning his instrument toward Jupiter, Galileo noticed tiny points of light that did not behave like ordinary stars. Night after night, they shifted position, dancing around the planet with patient watching. He realized they were moons, circling Jupiter itself. Not everything, then, circled Earth. Somewhere far away, a miniature system spun on its own, quietly defying the geocentric story. When Galileo studied Venus, he saw it change shape over time, swelling from a slim crescent to a nearly full disk, and back again. Those phases made sense if Venus orbited the Sun, catching different angles of its light, but they were almost impossible to reconcile with an Earth-centered universe. The observations were simple, almost gentle, but the implications were sharp. Piece by piece, the sky was whispering that Copernicus had been right. Galileo did not keep these whispers to himself. He wrote in Italian rather than Latin, so that ordinary readers could follow along. He argued that the sun-centered, or heliocentric, model was not merely a useful idea, but the best picture of reality. That confidence brought him into increasingly direct conflict with the Church. In the year 1616, Church authorities formally declared that the heliocentric view contradicted Scripture and instructed Galileo not to teach it as truth. For a while, he stepped back, at least in public. Yet the question smoldered. Years later, he published a lively book presenting a conversation between characters who defended different world systems. The structure was playful, but the message was clear. The sun-centered view came out looking wiser, and those who clung to the old geocentric model were made to seem foolish. This time, Church patience ran out. Galileo was summoned to Rome, questioned, and pressed to recant. Under the weight of power and age, he agreed to deny, aloud, that Earth moved. According to legend, as he left the courtroom, he murmured, "And yet it moves." Whether he actually said the words does not change the feeling behind them. He spent the rest of his life under house arrest, watched over, his skybound curiosity officially confined. But the ideas he had illuminated with his telescope continued to travel freely, passed from mind to mind, whispered about in letters, built upon by others. What Copernicus had dared to suggest, and Galileo had dared to see, unsettled people far beyond the walls of any observatory. If Earth was no longer the still center, perhaps humanity was no longer the crown of creation. If the heavens followed natural, measurable laws instead of perfect, unchanging patterns, then the universe might be a place of motion, change, and vast indifference. For some, that thought was frightening, a cold wind blowing through a once cozy cosmos. For others, it was a strange kind of comfort, an opening of the sky. New thinkers stepped into that opening. Johannes Kepler found elegant paths for the planets, not perfect circles, but stretched, elliptical orbits that matched observations with eerie precision. Isaac Newton later described gravity in a way that knit falling apples and orbiting moons into the same quiet law. Slowly, the universe shifted from a stage for divine geometry into a place that could be measured, tested, and described, even if it remained full of mystery. The Church did not lift its bans overnight. Suspicion and caution lingered for centuries. The struggle was never only about planets and orbits. It was also about who had the right to say what was true. By the early 20th century, another, softer question had begun to form in the back of astronomers' minds. How big is everything, really? Many believed that the Milky Way was the whole of the universe, a grand but self-contained island of stars stretching across the night. The faint cloudy smudges scattered here and there were called nebulae and were thought to be gas clouds or small gatherings of stars within our own galaxy. Yet some of those smudges, especially the spiral ones, looked oddly structured, almost like whirlpools of stars in their own right. Two astronomers, Harlow Shapley and Heber Curtis, found themselves on opposite sides of this quiet puzzle. In the year 1920, in a hall in Washington, D.C., they presented their views in what later came to be called the Great Debate. Shapley believed the Milky Way was enormous, much larger than many of his peers had imagined, and that everything we saw, including the spirals, lived inside it. He used special stars that pulse in brightness, called Cepheid variables, to trace distances to globular clusters and map the outline of our galaxy. His work painted the Milky Way as a vast city of stars, and our sun as a resident far from the center. Curtis, looking closely at photographs of the spiral nebulae, was drawn to a different conclusion. To him, their shapes, dark lanes, and bright cores resembled the Milky Way seen from afar. Their motions did not quite fit the idea that they were nearby clouds. He suspected they were separate island universes, other galaxies scattered at unimaginable distances beyond our own. There was no dramatic verdict at the end of that evening. No bell rang to announce a winner. The universe, for the moment, remained somewhere between Shapley's large but self-contained Milky Way and Curtis's grand, many-galaxy vision. The answer waited, quiet and patient, in the light of a few particular stars. A few years later, a young astronomer named Edwin Hubble climbed to the summit of Mount Wilson in California, where the Great Hooker Telescope, a 100-inch eye of glass and steel, was aimed at the night. He turned this powerful instrument toward the Andromeda Nebula, one of the brightest and most beautiful spirals in the sky, and searched its hazy glow for something familiar. Within that distant swirl, he found a Cepheid variable, one of the same kind of pulsing stars others had used to measure distances inside the Milky Way. By carefully tracking its rhythm and using the relationship between its pulse and its true brightness, Hubble could estimate how far away it was. When he worked through the numbers, the result was staggering. Andromeda was not a nearby cloud at all. It lay more than 2 million light-years beyond us. It was an entire galaxy. Almost at once, the balance tipped, with Andromeda revealed as a separate galaxy, far beyond the Milky Way. Curtis's vision quietly became the one astronomers leaned toward. The universe was no longer a single island of stars. It was an ocean filled with islands, some close, some unimaginably distant, scattered in every direction. As more observations arrived, another truth emerged. These islands were not standing still. On the larger scales, they were drifting apart, the spaces between them slowly stretching. Looking back, that quiet debate in Washington feels like a doorway. No one won in the room that night, but the questions they raised cleared a path from a small, self-contained cosmos to the vast, expanding universe we talk about today. It showed how science often moves, not in thunderclaps, but through patient disagreement, careful argument, and the slow, steady gathering of evidence. And woven through it all was the quiet power of technology. Without the great telescope on Mount Wilson, Hubble's eyes would never have reached far enough to pick out that single pulsing star in Andromeda. Just as Galileo's fragile lenses had once brought the moons of Jupiter into focus, the Hooker telescope brought the sheer scale of the universe into view. The night sky, which had once been a hazy curtain of mystery, began to show layers. Astronomers saw distance, clusters, filaments, patterns. The stars were no longer scattered across one great disk. They lived in billions of galaxies, each a swirling city of suns, each with its own possibilities and silent stories. That widening of perspective did something gentle but deep. It invited people to ask larger questions and to let their imaginations stretch in step with the cosmos itself. Hubble did not stop with Andromeda. He turned that giant eye toward other galaxies and began to look not only at where they were, but at the light they sent. When that light was spread into a rainbow, it carried delicate signatures, dark lines where certain colors were missing, the fingerprints of elements inside the stars. But the lines were not quite where they should have been. They were shifted toward the red. This red shift had a familiar cousin in everyday life. When a train or a siren rushes toward you, the sound climbs higher. As it moves away, the pitch drops. Light behaves in a similar way. When a source comes toward you, its light is shifted very slightly toward the blue. When it recedes, the light is stretched toward the red. So, when Hubble and his colleague Milton Humason saw those spectral fingerprints nudge toward the red, it meant the galaxies were moving away. At first, it was only a curious pattern. Then Hubble began to compare many galaxies, measuring both their distances and their red shifts. A quiet relationship appeared. The farther away a galaxy was, the stronger its red shift, and the faster it seemed to be receding. This was not just a few strays drifting off. On the grand scale, everything was moving away from everything else. The universe was not static. It was expanding. It is a strange picture to hold in a sleepy mind. For centuries, people had imagined the universe as a fixed stage, with stars pinned in their places and galaxies, once discovered, turning like steady wheels. Even sun-centered models still kept space itself frozen, while planets traced their paths. Newton's laws described a vast cosmic clock, ticking on forever, but not swelling or shrinking. Now Hubble's data whispered something different. The very fabric of space was stretching. It is not like shrapnel from an explosion, with matter thrown outward into empty room. Instead, the room itself grows. A simple image is that of dots on the surface of a balloon. As you inflate it, every dot moves away from every other dot, not because they are crawling across the surface, but because the surface itself is expanding. From any dot's point of view, all the others seem to recede. There is no special center on the surface, only the shared expansion. So it is, as far as we can tell, with our universe. As this picture spread, it stirred more than astronomers' notebooks. If the universe is expanding now, then it must have been smaller in the past. If you mentally rewind the expansion, galaxies draw closer and closer, until you reach a time when everything we now see was compressed into a hot, dense state. This was the beginning of what would become the Big Bang idea. Not a bang in space, but the rapid unfolding of space itself from an earlier, fiery phase. Not everyone was ready to embrace a universe with a beginning. Many scientists preferred a steady-state cosmos, one that had no true starting point and no final end, always expanding yet always looking roughly the same on large scales. In that view, new matter would somehow appear as space stretched, keeping the overall density constant. It was neat, eternal, and felt more comfortable. But the redshift pattern refused to fit that story. The more carefully astronomers measured, the more stubborn the expansion appeared. Years earlier, Albert Einstein had written down his equations of general relativity. When he first applied them to the universe as a whole, they suggested that a perfectly static cosmos would be unstable, tending to expand or contract. Unwilling to give up the idea of a fixed universe, he added a term, the cosmological constant, to hold everything in balance. After Hubble's discovery, that extra term looked less like elegance and more like a patch. The universe did not need to be forced into stillness. It was moving on its own. From then on, cosmology became less a playground of pure speculation and more a careful, observational craft. Red shifts, distances, and faint glows from deep space turned into tools, like rulers laid across time. Because light takes time to travel, looking far away meant looking back into earlier chapters of the universe. Each distant galaxy became not only another place, but another moment, showing the cosmos when it was younger and denser. The universe no longer simply was, it had a history. An expanding universe suggested something quietly radical. If it had a past, it might have a birth. That thought opened new questions that reached beyond mathematics. What was that first state like? What set the expansion in motion? Could it ever stop, or reverse, or end in some distant, thin chill? The expanding cosmos did not answer these questions, but it made them real. The next great clue arrived as a soft hiss, not in visible light, but in microwaves washing gently from every direction in the sky. In the early 1960s, two radio engineers, Arno Penzias and Robert Wilson, were working at Bell Telephone Laboratories with a large horn-shaped antenna. It had been built for satellite communication, but they were using it to listen for faint radio signals from space. Whatever they did, they kept hearing a persistent, steady noise. It did not matter where they pointed the antenna, the hiss remained, smooth and uniform. They approached it like a problem. They checked the electronics, worried about interference from nearby cities, from the sun, from our own galaxy. They discovered that pigeons had made a home in the antenna and left droppings behind. Patiently, they cleaned everything out and encouraged the birds to find somewhere else to perch, hoping the stubborn noise would fade. But the background hum stayed. It was as if the sky itself were whispering in microwave tones. At the same time, a group of physicists at Princeton University, including Robert Dick and Jim Peebles, were thinking about the universe's beginning from a theoretical side. Decades earlier, George Gamow, Ralph Alpher, and Robert Herman had suggested that if the cosmos began in a hot, dense state, the leftover glow from that time should still be present, cooled and stretched by expansion into the microwave part of the spectrum. They had predicted a kind of fossil light, a relic, afterglow of the Big Bang itself, but their idea had mostly drifted in the shadow of the steady-state model. When news of Penzias and Wilson's puzzling signal reached the Princeton group, the pieces fell together. The engineers had accidentally found exactly the sort of glow the theorists were preparing to search for. The strange background hiss was not a flaw in the equipment. It was the cosmic microwave background, the CMB, the faint afterglow of the universe's birth, still filling all of space. This radiation had a temperature of only a few degrees above absolute zero, about 3 degrees on the Kelvin scale, and it arrived almost equally from every direction. It was just what a hot early universe would leave behind, after billions of years of cooling. 2 linked papers were published, one by Penzias and Wilson, carefully describing the noise they could not get rid of, and one by the Princeton group, explaining that it was likely the echo of creation itself. At first, some scientists hoped for alternative explanations. Perhaps distant stars or clouds of gas could be responsible. But as new instruments measured the CMB more precisely, those possibilities faded. The spectrum of the radiation matched almost perfectly what a simple, hot object would produce as it cooled a black body curve. It did not look like light from stars or dust. It looked like light from the universe itself. With that, the steady-state model lost most of its remaining support. The cosmic microwave background did not just nudge the scales toward the Big Bang, it pressed them down firmly. By the late 1970s, the picture of a hot, dense beginning had become the main framework for understanding cosmic history. And the CMB still had more to tell. In the 1990s, NASA's Cosmic Background Explorer satellite, usually called COBE, mapped the microwave sky in detail. Instead of a perfectly smooth glow, it revealed tiny ripples in temperature, slight warm and cool spots. Those faint blotches were the seeds of structure, places in the early universe where matter gathered just a little more densely than average, where galaxies and clusters would eventually grow. Later missions, like WMAP and Planck, traced those patterns with even greater clarity. From that delicate mottling of ancient light, scientists could read the universe's basic properties, its age, its overall shape, how much ordinary matter it contained, how much invisible dark matter, and how much mysterious dark energy was driving its expansion. The rate at which space was stretching, the balance of its ingredients, all were encoded in that soft, all-sky glow. None of this grand understanding would have unfolded quite the same way without that stubborn hiss in a horn antenna, the one that refused to disappear even after the pigeons were gone. What first felt like an irritation in the data turned out to be a message from when the universe was very young, a whisper of heat stretched thin by billions of years of expansion, a quiet glow filling all of space, a noise that turned out to be the oldest light in the universe. The cosmic microwave background became more than a faint hiss in an antenna. It turned into a kind of relic, a soft afterglow from a time when the universe changed forever, a frozen whisper from its hot, crowded youth, still bathing everything in a gentle wash of ancient light. Not everyone was comforted by this picture of a universe with a beginning. One of the sharpest skeptics was an English astronomer named Fred Hoyle. To him, the idea that all of space and time had once been squeezed into a tiny, fiery state, and then burst outward, felt not just strange, but almost unscientific. Hoyle loved order and continuity. In his mind, births and deaths of stars should follow patterns, and those patterns should not suddenly switch on at some mysterious first moment. He preferred a cosmos that had no true beginning and would never truly end. In this view, the universe was eternal and, on the largest scales, unchanging. New stars formed as old ones faded, galaxies drifted and evolved, but the overall picture stayed the same. This was the steady-state universe, smooth in the big view, forever renewing itself. For a while, it stood as a serious rival to the hot beginning that would later be called the Big Bang. Hoyle was not alone. In the late 1940s, he worked with Thomas Gold and Herman Bondi to shape this idea into a precise model. They accepted that observations showed expansion, but they added a clever twist. As galaxies moved apart and space stretched, new matter would appear in the gaps, slowly, quietly, At a rate too small to notice in any one place, fresh material would be created, later gathering into new stars and galaxies. The math could be made to work. The universe would grow, but its overall density would remain the same. On the largest scales, yesterday would always look like today and tomorrow. For many scientists uncomfortable with talk of cosmic birth, this was soothing. A steady-state universe did not require a moment of creation. It did not demand an answer to the question, what started it all? It simply was, and always had been. By contrast, the expanding, hot, origin universe felt abrupt, almost mythic. Meanwhile, another group of thinkers was walking a different path. Building on the work of Einstein and Georges Lemaitre, physicists like George Gamow, Ralph Alpher, and Robert Herman explored the idea that the cosmos really had begun in an extremely hot, dense state and expanded from there. They calculated that such a universe should still be filled with leftover light, stretched by expansion into the microwave part of the spectrum. Their prediction drifted quietly in the background for years. Ironically, it was Hoyle who gave this rival model its most famous name. On a BBC radio program in the late 1940s, he described the idea, somewhat dismissively, as the Big Bang Theory, hoping to highlight what he saw as its absurdity, a whole universe erupting from an almost unimaginable state. But the phrase was catchy. Listeners remembered it, and soon the name stuck. Hoyle did not simply grumble and move on. He spent years refining the steady-state model, answering criticisms, and pointing out what still troubled him about the hot origin picture. He disliked its reliance on unknown early conditions, and the way it seemed to suggest that everything came from nothing. To his ears, the language around a beginning sounded uncomfortably close to religious stories of creation. He wanted the universe to be governed by rules that did not need an unexplained starting gun. In his version of reality, matter was continuously created, a tiny drizzle of new substance appearing throughout space, too subtle to catch directly. It was a bold move, a new ingredient added to the recipe of physics. If it worked, it allowed the universe to expand while always retaining its large-scale sameness. For a time, the scientific community was split. The hot beginning explained many observations, but solid, direct proof was missing. The steady-state model felt elegant and eternal, even if it required new physics. Studies, debates, and heated conversations stretched on. Then the sky's oldest light entered the story. The discovery of the cosmic microwave background in the 1960s changed the balance. Here was that predicted relic radiation, glowing at just a few degrees above absolute zero, with a spectrum that matched a cooling, once hot universe. It was exactly the kind of afterglow the Big Bang model had anticipated. Steady-state supporters, Hoyle among them, tried to adjust. They proposed other sources for the radiation, variations of the model that might produce a similar signal, but none of those attempts fit the growing body of data. As observations became more detailed, the hot origin picture and the cosmic microwave background locked together like two pieces of the same puzzle. Slowly, the steady-state view faded from the center of cosmology. Hoyle remained unconvinced. He continued to publish, suggesting new forms of matter, new processes, anything that might keep alive the vision of a universe without a singular beginning. For him, it was not just stubbornness. It was a matter of principle. He believed that the cosmos should be described by timeless rules, not by a single abrupt event that felt too close to myth. To some, his persistence was heroic, a reminder that science needs voices willing to question its favorite stories. To others, he seemed simply unwilling to let go. Yet his resistance sharpened the conversation. By pushing hard against the Big Bang, he forced its supporters to gather more data, to refine their models, to answer difficult questions. In that way, even his refusal to accept a beginning helped make our picture of the universe stronger and clearer. While cosmologists were wrestling with the age and origin of everything, another quiet crisis was brewing in the way galaxies moved. In the middle of the 20th century, astronomy enjoyed a new sense of confidence. The expanding universe had become the standard view. Telescopes were sharper, instruments more sensitive. Newton's laws of motion and gravity, joined by Einstein's deeper framework, seemed to explain almost everything seen in the skies. The universe looked vast, but comfortably understandable. Then the galaxies misbehaved. Spiral galaxies, with their graceful pinwheel arms, turned out to be hiding a secret in the way they spun. Astronomers began to measure how fast stars orbited at different distances from a galaxy's center. According to the familiar pattern in our solar system, the farther out you go, the slower things should move. Mercury, close to the Sun, races along. Neptune, far away, creeps by comparison. Gravity weakens with distance, so orbital speeds ought to drop as you move outward. By that logic, stars near the edges of a galaxy should drift more slowly than those near the bright core. But when astronomers looked carefully, that gentle decline simply was not there. In the 1970s, Vera Rubin, working with Kent Ford and a sensitive spectrograph, traced the speeds of stars and gas in the outer regions of many spiral galaxies. The results were startling. The stars at the edges were not slowing down. They were circling the galaxy at almost the same speed as stars, much closer to the center. In some cases, they moved even faster. According to the usual calculations, that should not be possible. If the only mass in a galaxy were the visible stars, gas and dust, gravity would not be strong enough to hold those fast-moving outer stars in place. They should be flung off into the darkness, yet there they were, staying bound. Something unseen seemed to be adding extra gravity, something spread through and around each galaxy, tugging on the stars but not shining like ordinary matter. Rubin's measurements were careful and repeated across many galaxies. The pattern kept appearing. Instead of rotation curves that dipped with distance, they stayed flat. Either our understanding of gravity was failing at these scales, or there was more mass than anyone could see. Astronomers reached for a name and settled on dark matter. The phrase had been used before in a looser way, but now it took on a sharper meaning. Dark matter was not just any unknown material. It was a specific kind of unseen mass that did not emit or reflect light, yet still exerted gravity. It could not be made of ordinary dim stars or cold gas, because those would show up in other observations. Whatever it was, it did not interact with light at all. It was dark in the deepest sense. Years earlier, in the 1930s, a Swiss astronomer named Fritz Zwicky had noticed something similar on much larger scales. Studying the Coma cluster, a vast gathering of galaxies, he found that they were moving so quickly that the whole cluster should have flown apart if only the visible matter were there to hold it together. By his estimates, the cluster needed far more mass than telescopes could see. He also called this missing stuff dark matter. But at the time, his claims were easy to dismiss. Zwicky had a reputation for being eccentric, and the tools were not yet in place to test his idea thoroughly. Rubin's quiet, persistent work changed that. Her data were precise, her methods transparent, and they arrived in an era when astronomy was ready to check and recheck the numbers. As more galaxies were measured, the same story emerged. The missing mass problem grew busier. Elliptical galaxies, galaxy clusters, and even the vast cosmic web tying structures together, all seem to require far more mass than what glowed in starlight. Some physicists tried a different route. Perhaps gravity itself behaved differently on large scales. They proposed modified gravity theories, where Newton's familiar law would bend or shift in the gentle outskirts of galaxies. These ideas could explain some rotation curves, but they struggled to account for all the evidence at once. Dark matter, as strange as it sounded, offered a simpler, more unified explanation. An invisible halo of mass surrounding galaxies and clusters, holding fast-moving stars and galaxies in place with its unseen pull. Other lines of evidence joined in. Gravitational lensing, the way massive objects bend the path of light, showed that many galaxy clusters had far more mass than their visible contents could explain. The way the cosmic microwave background is patterned across the sky also depends on how much matter the early universe held. Those delicate ripples in the CMB suggested that there is roughly 5 times more dark matter than ordinary matter in the cosmos. Again and again, the universe pointed to the same conclusion. Most of its mass is hidden. What dark matter is, however, remains an open question. Scientists have imagined whole families of possible particles, weakly interacting massive particles, often shortened to WIMPs, ghostly axions, subtle sterile neutrinos, even swarms of small black holes. Experiments deep, underground, on high mountain peaks, and in space, are all trying to catch the faintest hint of a dark matter particle bumping into ordinary matter or leaving some tiny trace. So far, the searches have been met with silence. The models are revised, the detectors made more sensitive, and still nothing reveals itself. Yet the evidence in the sky remains. Galaxies spin in ways that visible matter alone cannot explain. Clusters of galaxies cling together more tightly than their starlight allows. The cosmic web and the CMB both whisper the same thing. Something heavy and unseen is shaping the universe. The missing mass crisis did not close with a neat answer. It opened a deeper mystery. Night after night, telescopes watch stars at the edges of galaxies circle with impossible speed. The equations say they should fly apart. The images show them holding on. Whatever dark matter turns out to be, one stubborn fact remains, written in the quiet motion of countless suns. The stars still spin too fast. The galaxies still cling together, and the universe still pulls in ways that visible matter alone cannot explain. Whatever it is, dark matter seems to be out there, quiet and invisible, yet essential, like a hidden scaffold holding the cosmic structures in place. In the early 2000s, astronomers met a different kind of puzzle, a riddle about time itself, in the form of a single, rather ordinary star in our own galaxy. It was not especially bright or dramatic, but when scientists tried to tell how old it was, the answer came back unsettling. The star, catalogued as HD 140283 and nicknamed the Methuselah star, seemed to be older than the universe itself. At that time, careful measurements of the cosmic microwave background and the rate at which space is expanding suggested that the universe is about 13.8 billion years old. The Methuselah star, by contrast, appeared to be around 14.5 billion years old, give or take about 1 billion years. Even allowing for that margin of error, its minimum age sat uncomfortably close to, or even a little above, the age of everything. To weigh its age, astronomers studied more than just its brightness. They examined its color and, most importantly, its chemical recipe. In astronomy, anything heavier than helium is called a metal. The Methuselah star turned out to be extremely poor in metals, almost purely made of hydrogen and helium. That usually marks a star as very old, born when the cosmos had not yet been enriched by many generations of exploding stars. They then placed it into models of stellar evolution, the quiet life stories that show how stars of different masses and compositions change as they burn their fuel. On those charts, the Methuselah star looked as though it had been shining for almost as long as time itself, igniting not long after the universe began to cool and form the first stars. That is where the tension appeared most sharply. The star and the universe seemed to share almost the same birth year. There were obvious places to look for mistakes. Perhaps the models of stellar interiors were missing some subtle piece of physics, a small effect that could make a star appear older than it truly is. Distance was another suspect. If the Methuselah star was a little closer than astronomers thought, it would be slightly brighter than it appears, and thus younger than early calculations suggested. Many researchers pointed out that, within the uncertainties, the star's age might still fall just below the age of the universe. Yet the closeness of the two numbers, almost touching, made people uneasy, like seeing two clocks that are supposed to agree ticking just a fraction out of step. This discomfort fed into a larger tension already growing in cosmology. Different ways of measuring the age and expansion of the universe do not always line up. Using the cosmic microwave background gives one value. Measuring the expansion rate in the nearby universe, a quantity called the Hubble constant, can give another. Depending on which method you trust more, the universe may come out slightly younger or slightly older. The Methuselah star sits in the middle of this disagreement, a quiet reminder that our cosmic clocks may not all be calibrated in quite the same way. The Methuselah star is not entirely alone. Astronomers have found a small population of similarly ancient, ultra-metal-poor stars in the halo of the Milky Way, that faint, spherical cloud of old stars surrounding the bright disk. These fragile suns likely belong to the very first generations to ever exist, born when the universe was still young and almost entirely made of hydrogen and helium. Studying them is like peering through a keyhole into a much earlier time, each one a fossil still burning from an age when galaxies were only beginning to assemble. While these quiet elders raise questions about ages and beginnings, other ideas push at the edges of time itself. One of the strangest comes from the same equations that gave us black holes, the idea of white holes. If a black hole is a region where everything falls inward and nothing comes back out, a white hole is its mirror image, at least on paper. Instead of swallowing matter and light, it would fling them outward, never allowing anything to enter. The story starts with general relativity, Einstein's description of gravity as the bending of space-time. Soon after he wrote down those equations, Karl Schwarzschild found a solution that described what we now call a black hole, with an event horizon acting as a one-way door and a singularity lurking at the center. When physicists looked more carefully at this solution, they noticed that, mathematically, there was another side to it that behaved like the opposite of a black hole. Out of that mirror side came the notion of a white hole. At first, white holes were treated as curiosities, strange shapes hiding in the math. No telescope had ever seen one, and nothing in nature seemed to require them. But the equations did not forbid their existence. And in physics, that is sometimes enough to keep an idea alive. The trouble is that white holes run awkwardly against the flow of time we experience. If you reverse the direction of time in the equations for a black hole, you get something that looks like a white hole, where one is formed by collapse. The other would appear suddenly, spewing matter outward without any clear cause. Most physicists are uncomfortable with that. Our everyday world is full of arrows of time. We remember the past, not the future. Broken cups do not leap back together. Stars form, burn, and die. A white hole would be like the universe playing a scene in reverse for no apparent reason. It seems to violate the usual sense of cause and effect, demanding conditions so precise that they feel almost impossible. For that reason, many think white holes do not exist in the real cosmos, even if the equations quietly allow them. Others prefer to leave a little room for surprise. After all, black holes themselves were once considered too strange to be real. For decades, even Einstein doubted that nature would permit such extreme objects to form. He saw the singularities at their centers as signs that the theory had been stretched beyond its proper domain, not as predictions of actual things in the sky. The idea of a black hole came from the same Schwarzschild solution, describing what happens when enough mass is crushed into a small enough volume that the escape speed at a certain radius exceeds the speed of light. That radius marks the event horizon, a boundary from which not even light can return. Inside, space curves inward, and time itself seems to point toward the center. For a long time, many physicists treated this as an abstract warning, rather than a description of real stars. In 1939, Einstein even published a paper arguing that, under realistic conditions, collapsing matter would never quite form a true black hole. He believed that nature would find a way to avoid such extremes, that pressure or some new effect would halt the collapse before an event horizon could fully appear. At the same time, though, J. Robert Oppenheimer and Hartland Snyder were reaching a different conclusion. They showed that if a star were massive enough and ran out of the fuel that supports it, gravity would win. Nothing known could stop the collapse. The star would shrink, its surface falling inward faster and faster until it crossed its own event horizon and vanished from view. To a distant observer, the star would seem to slow and dim, freezing at the edge. From its own point of view, it would continue inward toward the singularity. Even with this work, black holes remained more theory than reality for decades. There were no instruments sensitive enough to spot them, no clear signatures to look for. People used phrases like frozen stars and gravitationally collapsed objects instead of the more dramatic term we know today. It was not until the 1960s, as radio and X-ray astronomy opened new windows on the sky, that possible black holes began to appear in the data. Mysterious, compact sources like Cygnus X1, which seemed to be a heavy, invisible companion stripping matter from a nearby star, gave astronomers their first serious candidates. As in falling gas spiraled toward the unseen object, it heated up and shone in high-energy light, just what you would expect from material being pulled into a deep gravitational well. By the early 1970s, black holes had stepped out of the realm of pure theory and into the everyday work of astrophysics. Researchers explored their properties in detail, showing how they spin, how they can merge, and how quantum effects might cause them to lose mass very slowly over unimaginable spans of time. The same equations that once seemed untrustworthy in their extremes became tools for probing deep questions about space, time, and information. The road to that acceptance was long. For much of the 20th century, the idea of regions where space collapses and time twists on itself clashed with a gentler picture of a balanced universe. Even Einstein, who gave us the equations, doubted that their wildest predictions would ever be realized. Yet the universe proved more adventurous than he had hoped. Now, black holes seem to be everywhere. We see their fingerprints at the centers of galaxies, in the bright engines of quasars, and in the ripples of space-time we call gravitational waves when they collide. And still, Even as we map their shadows and trace their influence, they remain among the strangest puzzles we know, quietly guarding whatever secrets lie beyond the event horizon. Neutron stars sit in a strange middle ground between life and collapse. They are the compressed hearts of massive stars that once exploded in brilliant supernovae cores, left behind when gravity squeezes matter into a tight knot only a few kilometers wide, yet heavier than our sun. Inside them, atoms lose their familiar shapes. Protons and electrons are pressed together into neutrons until the whole star becomes one immense sphere of nuclear matter, dense beyond imagining. For a long time, astronomers believed there was a clean boundary between these objects and black holes. A neutron star, they thought, could only grow so heavy before gravity won. This tipping point, the Tolman-Oppenheimer-Volkoff limit, marked the line where neutron pressure could no longer hold back collapse. Stay below it, and the star lived on as a neutron star. Cross it, and it would fall inward into a black hole. But as observations sharpened, something unexpected emerged. A handful of neutron stars were found to be heavier than theory allowed, too massive to survive, yet still shining, still spinning, still whole. One early hint came from a neutron star discovered in 2010, part of a binary system whose radio pulses let astronomers measure its mass with precision. It turned out to be roughly twice the mass of the Sun. That number pushed beyond the comfort of theory. Another, found soon after, hovered around a similar mass. In 2019, yet another was measured at slightly above that, one of the heaviest neutron stars ever recorded. Each new finding nudged the boundary further, challenging the idea that there was a simple line between neutron stars and black holes. According to the usual physics, gravity at these masses should crush even the neutrons themselves. Yet these stars remained intact. What holds such an object up is not heat or fusion. Those have long since ended. The only thing resisting collapse is neutron degeneracy pressure, the quiet quantum rule that neutrons, like electrons, refuse to share identical states. But even that rule has limits. At extreme densities, the pressure should fail. So why do these heavy stars persist? One possibility is that inside them, neutrons may break down into quarks, the smaller particles inside protons and neutrons. If that happens, the star might become a quark star, a more exotic state of matter that can resist collapse better than pure neutron matter. Another idea is that the equation of state, the relationship between pressure and density in nuclear matter, may not be what we thought. We cannot recreate such crushing pressures in any lab, so models rely on theory and indirect clues. If nuclear forces behave differently at these depths, neutron stars may withstand more mass than scientists expected. Some of these massive stars are magnetars, neutron stars wrapped in magnetic fields, billions of times stronger than anything on Earth. Such fields might add a kind of support, slowing collapse in ways we do not yet fully understand. Rotation also plays a role. A spinning star can carry slightly more mass, the centrifugal force giving the faintest extra push against gravity. Perhaps some of these heavy stars are caught in a temporary balance, supported by their rapid spin. Over time, as they lose energy and slow down, they may eventually collapse. But the number of these massive neutron stars suggests their stability may not be a mere moment of luck. What all of this shows is simple and humbling. We still do not fully understand what happens inside neutron stars. They act as natural laboratories for the universe's most extreme physics pressure, gravity, and quantum rules tangled together in ways we can hardly simulate. Each new observation adds a little more tension to the theories that once felt settled. The neat boundary between neutron stars and black holes is dissolving, becoming a wide twilight zone where unfamiliar forms of matter might live. Gravitational waves have added new clues. When neutron stars merge, their collision sends ripples through space-time. One such event, detected in 2017, revealed the masses and shapes of the stars before they collided, and hinted at what formed after. Some models suggest the final object might have been a hypermassive neutron star, again pushing past what was thought possible. As these questions grow louder, astronomers turn their eyes toward our own galaxy's center, where an entirely different mystery lies. Buried beneath swirling clouds of dust and gas, at the heart of the Milky Way sits a supermassive black hole known as Sagittarius A star. It is millions of times the mass of the Sun, powerful enough to tug stars into tight, rapid orbits. We know its presence from the way nearby stars whip around an unseen anchor, and yet, for all its weight and influence, Sagittarius A star is astonishingly quiet. Many galaxies host black holes at their centers, and in countless cases, those black holes blaze like cosmic beacons. When they feast on infalling gas, the matter heats up and shines across the electromagnetic spectrum. Some become so bright they outshine all the stars around them, creating active galactic nuclei. The Milky Way's core, however, rests in an unusual calm. Sagittarius A star flickers only faintly, waking in brief bursts before settling again into near silence. One explanation is simple. Perhaps it lacks fuel. Having gas nearby is not enough. For matter to fall into a black hole, it must slow down, lose angular momentum, and spiral inward. If it keeps its speed, it simply circles around. The gas near the center of our galaxy may be too hot, too turbulent, or too tangled in magnetic fields to drift inward. It may also be stirred by winds from nearby stars or remnants of ancient supernovae, preventing it from cooling and sinking toward the black hole. Yet Sagittarius A star is not entirely silent. Occasionally, telescopes like Chandra see sudden flares, brief flashes of X-rays, hinting that small pockets of matter do fall in, sparking short-lived brightness. These moments, though rare, show that the black hole is still alive, still hungry, just not fed in any steady way. There are clues that Sagittarius A star has not always been so mild. High-energy structures called the Fermi bubbles rise above and below the Milky Way like enormous glowing balloons. They stretch tens of thousands of light years and seem to have been formed by a burst of power from the galactic center millions of years ago. Light echoes reflected from nearby clouds also hint that Sagittarius A star flared far more brightly a few centuries ago, enough to cast shadows across regions of gas that are only now revealing those flickers. Why, then, so quiet now? Part of the answer may lie in the Milky Way's serene history. Some galaxies experience violent mergers that funnel great rivers of gas toward their centers, waking their black holes in dramatic fashion. But the Milky Way has avoided major collisions for a long time. Without the chaos of merging galaxies to drive gas inward, our central black hole may simply drift through a long, quiet phase. Around Sagittarius A star, a cluster of stars sweeps by in tight, fast orbits. Astronomers have tracked their movements for decades, mapping the shape and mass of the invisible object at the center. These stars come close, but not close enough to fall in. Their graceful loops suggest that, for now, the environment near the black hole is stable, almost calm, shaped not by violent feeding, but by delicate balances of motion, pressure, and temperature. Scientists continue to watch, running simulations, studying magnetic fields, examining gas flows, and wondering how long this quiet might last. Every new insight brings the galactic center into slightly sharper focus, even as it leaves behind another layer of mystery. One more reminder that even the calmest places in the universe can hold the deepest secrets. The black hole at the heart of the Milky Way does more than pull on stars and gas. It pulls on our curiosity. Somewhere ahead in time, it may wake again. A drifting cloud of gas, or an unlucky star, could wander too close and trigger a bright new feeding phase. For now, though, Sagittarius A star is a sleeping giant, a cosmic engine at rest, reminding us that even the quietest places in the universe can be holding their breath. When astronomers turn their telescopes to the most distant reaches of the sky, they are also looking backward in time. Light from those faraway objects has traveled for billions of years to reach us, carrying images of the universe when it was young. In those early chapters, just a few 100 million years after the Big Bang, theory once painted a picture of small, messy, slowly assembling galaxies. But that is not quite what the deepest observations are showing. Instead of only tiny, tentative structures, astronomers are finding massive, surprisingly mature galaxies in the early universe systems that seem too big, too soon. Some appear to be as heavy as the Milky Way, or even more so, yet they are seen when the universe was only a small fraction of its current age. In the standard story, galaxies start as little clumps of gas, form stars at a modest pace, and grow through slow mergers and steady infall over billions of years. So when a young universe already contains large, well-formed galaxies, it nudges that story out of shape. The James Webb Space Telescope has made this tension sharper. With its sensitive infrared eyes, it can see the faint glow of very distant galaxies, whose light has been stretched by expansion into longer wavelengths. Almost as soon as it began returning data, James Webb revealed bright, hefty galaxies from times only a few 100 million years after the Big Bang. Some estimates suggest they may hold tens of billions, perhaps even around 100 billion solar masses in stars. A few show reddish colors that hint at older stellar populations, and in some cases, hints of ordered disks rather than only clumps. If these measurements hold up, it means that within less than 1 billion years, gas had not only gathered, but rapidly built stars, settled into shape, and in some cases may even have slowed its own star formation. That speed is hard to reconcile with models that expect a more gentle rise. There are ways to soften the shock. It may be that early galaxies were simply more efficient at turning gas into stars, that conditions then allowed a kind of cosmic growth spurt. Or it could be that our methods for estimating mass and age from starlight, tuned on nearby galaxies, mislead us slightly when applied to such remote, pristine systems. If the stars in those galaxies behave a bit differently from what our models assume, their true masses could be lower than first reported. Even so, many researchers think the basic surprise will remain. Early galaxies still look, overall, larger and brighter than anticipated. That raises the possibility that something about the early universe itself might differ from our expectations. Perhaps dark matter clumped more quickly, or the initial ripples in density were stronger in some regions, letting structures form faster. Adjusting those details would ripple through other parts of cosmology, including our understanding of when the first stars relit the universe in the era of reionization. As observations accumulate, the picture growing from James Webb and other observatories is not of a sleepy, slowly awakening cosmos, but of an early universe that was already busy and crowded, racing to build its first great islands of light. The story becomes even stranger when we look not only at how fast galaxies formed, but at what they are made of. For years, the galaxy called Dragonfly 44 seemed like a perfect poster child for dark matter, discovered with a special array designed to spot very faint objects. It appeared as a ghostly smear in the Coma cluster, about a few 100 million light-years away. It turned out to be roughly the size of the Milky Way, but with only a sprinkling of stars. Most of its mass, early studies suggested, had to be invisible. The stars inside moved quickly enough that the galaxy should have torn itself apart, unless an enormous halo of dark matter was holding it together. The idea fit comfortably with the standard picture. Dark matter as the unseen skeleton on which galaxies are built. But then, a few years later, came reports of other ultra-diffuse galaxies that seemed to flip the script. In a small group of galaxies associated with a larger neighbor, astronomers identified systems similar in size and brightness to Dragonfly 44 that appeared to contain very little dark matter at all. The motion of their stars could be explained almost entirely by the visible mass. No hidden halo was required. That contrast was unsettling. If one faint galaxy could be almost all dark matter, and another of similar type could be almost free of it, what did that say about the rules of galaxy formation? Some argued that the measurements might be off, that distances, star velocities, or the influence of nearby galaxies could have been misjudged. Others suggested a more physical story. Perhaps these odd galaxies once had dark matter halos, but lost much of them through close encounters and tidal stripping in dense environments. Their invisible scaffolding peeled away while their stars remained. At the same time, follow-up work on Dragonfly 44 itself suggested that its dark matter fraction might have been overestimated. Revised measurements of its star clusters and stellar speeds lowered its total mass, making it still dark matter rich, but not as extreme as first imagined. Instead of one clear moral, astronomers were left with a more tangled tapestry. Some diffuse galaxies with a lot of dark matter, others with surprisingly little, and a need to refine both observations and theory. These strange galaxies also brush up against alternative ideas like modified gravity, where the laws of motion are adjusted instead of adding dark matter. If a galaxy truly behaves in a perfectly Newtonian way without needing hidden mass, that can be awkward for models that expect modified gravity to show its hand in every low acceleration system. In their own quiet way, these faint smudges of starlight challenge both the dark matter paradigm and its main competitors, encouraging more careful work on all sides. Stories like these of monster galaxies in the early universe, of dark matter-rich ghosts and dark matter-poor outliers, echo an older lesson that first unfolded much closer to home, in the orbit of Mercury. In the 19th century, astronomers noticed that Mercury's path around the Sun did not quite match Newton's predictions. Its orbit is an ellipse, as expected, but the point of closest approach to the Sun, the perihelion, slowly drifts over time. Most of this precession could be explained by the tugs of other planets. Yet, even after those effects were carefully subtracted, a small leftover remained, amounting to about 43 arcseconds per century, tiny on the sky, but stubborn. At the time, Newton's gravity had a powerful reputation. It had described planetary motions with exquisite accuracy and helped predict the existence of Neptune by explaining quirks in the orbit of Uranus. So when Mercury misbehaved, many assumed the problem must be an unseen object, another planet. orbiting even closer to the Sun, whose gravity nudged Mercury just enough to cause the extra precession. That hypothetical world was given a name: Vulcan. For decades, observatories searched for Vulcan. Astronomers reported brief sightings of dark dots crossing the Sun during eclipses or at dawn and dusk, but the dots never lined up into a consistent orbit. Sometimes they vanished, sometimes they appeared in the wrong place. The supposed planet remained a shadow, always invoked, never confirmed. The puzzle lingered until a new way of thinking about gravity arrived. In the early 1900s, Albert Einstein developed general relativity, recasting gravity not as a force between masses, but as the curvature of space-time itself. Under this fresh framework, planets do not just feel pulls, they follow paths shaped by the geometry around them. When Einstein applied his equations to Mercury, the extra precession fell out naturally. The theory predicted exactly the missing 43 arcseconds per century. No hidden planet was needed. With that, Vulcan quietly dissolved. After half a century of searching, the missing mass problem in Mercury's orbit turned out to be a sign that the old theory needed to give way to a deeper one. The planet that astronomers had invented existed only inside a framework that could not handle the reality of space near the Sunday. Once the framework changed, the planet disappeared. That story still echoes in modern debates about dark matter, monster galaxies, and quiet black holes. Sometimes, missing mass really is missing. Adding an unseen ingredient like dark matter helps the equations match what we observe. Other times, as with Mercury, the universe is hinting that our rules are incomplete. The only way to know which is to keep watching, keep measuring, and stay willing to let go of even our most cherished ideas when the sky whispers a different truth. The rise and fall of Vulcan is one of those rare stories where a world was born entirely on paper, treated as real, searched for in the sky, and then gently erased by a better idea. For many astronomers, it lingers as a soft warning. Sometimes the thing we are missing is not another planet, but a new way of seeing gravity itself. Far from Mercury's orbit, other surprises waited, this time around distant suns. When astronomers first began finding planets beyond our solar system in the 1990s, they quietly expected the cosmos to echo what we knew at home. Small, rocky worlds snug around the star, big gas giants lounging far away where it is cold enough for their thick atmospheres to survive. Our own system seemed like a sensible template. Close in, the young sun's heat would have driven light gases away, leaving heavy rock and metal to build worlds like Earth. Farther out, beyond the frost line, gas giants like Jupiter and Saturn could gather icy material and hold on to vast envelopes of hydrogen and helium. Then the first discoveries arrived and calmly ignored that script. The first confirmed planet around a sun-like star, 51 Pegasi b, announced in the mid-1990s, was a gas giant not unlike Jupiter in mass. But it circled its star in just a few days, so close that its day side would have been seared by intense starlight. It was a Jupiter-sized planet, hugging its star so tightly that, by older theories, it should never have formed there at all. Soon, more planets of the same kind appeared. Large, gaseous worlds on tiny orbits, some whipping around their stars in only a handful of days. They came to be called hot Jupiters. The puzzle was straightforward and unsettling. The inner regions near a young star should be too hot for gas giants to assemble. Building one there was like trying to stack snow into a snowman on a hot stove. Something in our picture of planet formation had to bend. One idea rose quickly to the surface. Perhaps these giants did not form where we now see them. Maybe they grew far out in the cool parts of the protoplanetary disk, like Jupiter did, and then slowly migrated inward. Astronomers had considered migration before, but as a rare footnote, the hot Jupiters forced it into the main story. Interactions with the surrounding gas, or gravitational tugs between planets, could steal orbital energy little by little, letting a giant world spiral inward until it parked in a tight, close orbit. As observations improved, another layer of strangeness emerged. Using a technique called the Rossiter-McLaughlin effect, astronomers could measure how a transiting planet blocks different parts of a spinning star's surface, revealing the angle between the star's spin and the planet's orbital path. In a calm, textbook system, those should be aligned, the way all major planets in our solar system orbit in the same direction that the Sun rotates. For some hot Jupiters, that was true. For others, it was not. A growing number were found on steeply tilted paths. A few looped around in the wrong direction entirely, orbiting backwards relative to the star's spin. Under the classic picture, planets are born in a flat, rotating disk. Their orbits inherit that disk's direction. To flip a planet, something dramatic has to happen after birth. Theorists began to imagine wilder histories. Perhaps a distant companion star tilted the system and slowly torqued the orbit of the planet, sending it on a looping, highly inclined path that later shrank and settled close to the star. Perhaps two or more giant planets once danced together, came too close, and scattered one another, one flung outward or even ejected into interstellar space, another hurled inward on a crooked orbit. Over time, tidal forces between the star and this unlucky survivor could circularize the orbit, locking it into a tight embrace, even if it remained misaligned or retrograde. In these stories, planetary systems do not grow quietly. They jostle, collide, and rearrange themselves, leaving behind hot Jupiters as scarred survivors of earlier chaos. That has sobering implications for smaller, Earth-like worlds. In many simulations, a giant migrating inward wreaks havoc on any inner rocky planets, either swallowing their building material, kicking them into the star, or flinging them out of the system altogether. If that is common, then systems with hot Jupiters may be poor cradles for Earth-like, stable worlds. And if some smaller planets do survive, they may inhabit strange, elongated orbits far different from our own gentle path. At the same time, hot Jupiters have become laboratories. Their large sizes and short orbital periods make them easier to detect, and their extreme environments are ideal for testing ideas about how atmospheres behave under intense heating, how tidal forces strip away gas, and how planets slowly spiral inward toward eventual destruction. Some are bloated and puffed up, as if the heat has swollen them beyond what models predict. Others trail long, comet-like tails of escaping gas, caught in the act of being peeled away by starlight. These worlds quietly rewrote the normal template for planetary systems, reminding us that our solar system, tidy as it seems, may be more of an exception than a rule. Strange planets were not the only things bending expectations. One ordinary-looking star in the constellation Cygnus turned out to behave in a way that tugged at the edges of imagination itself. The star, catalogued as KIC 8462852 and nicknamed Tabby Star after astronomer Tabitha Boyajian, was one of hundreds of thousands monitored by NASA's Kepler spacecraft. Kepler watched for tiny, regular dips in brightness, soft blinks that usually signal a planet passing in front of the star. Most of the time, these dimmings are small and predictable, repeating with clock-like precision. Tabby's star did something else. Its light would sometimes drop by a few percent, sometimes by nearly 20%, lingering dim for days before recovering. The dips were irregular, not repeating on a neat schedule, and they differed in depth and shape. No simple pattern emerged. One dip might be shallow and brief, another deep and sprawling. This was not how ordinary planets behave. Even a large planet like Jupiter blocks only a small fraction of its star's light, and it does so with a steady rhythm. The star did not look especially young. There was no obvious, thick disk of debris that might explain such dramatic flickering. At first, teams explored natural explanations. Perhaps a swarm of comets breaking apart. Perhaps clouds of dust. Perhaps a disrupted ring system, or fragments from a shattered world. Some even wondered if Kepler's instruments were at fault. But cross-checks suggested the signal was real. In the original scientific paper, one possibility was mentioned almost in passing, perhaps in some extremely unlikely scenario. The dimming came from large artificial structures built by an advanced civilization, something like a Dyson swarm, a loose collection of energy-collecting panels orbiting the star. That idea was never the favored explanation among astronomers, but when the phrase alien mega-structure appeared, it leapt into headlines. The public's imagination did the rest. Behind the excitement, the work continued in a quieter key. New campaigns raised money to monitor the star from the ground, watching in multiple colors of light. If solid, opaque objects were blocking the star, they would dim all wavelengths equally. If dust was responsible, shorter wavelength light would be blocked more strongly than longer wavelength light. When Tabby's star dipped again under this careful watch, the dimming turned out to be wavelength dependent. That pointed toward dust rather than solid panels. The dust explanation eased the need for more exotic ideas, but it did not close the case. The source of that dust remained mysterious. The star did not clearly wear the wide, bright disk of a typical young system. So astronomers sketched out other scenarios: a disrupted planet or moon torn apart and slowly smeared into orbit, a population of comets disturbed from a distant reservoir and dragged inward, clumpy shells of material on a tilted path, passing in front of the star in complex ways. Tabby's star became a kind of mirror for how science handles the unknown. First, you test the data. Then, you search for natural explanations, layering model upon model. Only when those possibilities struggle do the more speculative ideas get airtime. In this case, the mention of a megastructure helped attract attention and resources, even as most researchers quietly leaned toward dust and debris. It also broadened the conversation about techno-signatures, possible signs of advanced civilizations that might show up not only as radio signals, but as odd energy patterns or engineered shadows. Kepler could show that something was crossing the star, but not exactly what. Other telescopes, in space and on the ground, have added pieces, but no simple picture has emerged. It is possible that future instruments, perhaps the James Webb Space Telescope or its successors, will gather enough detail to settle the matter. It is also possible that Tabby's star will remain an outlier, a singularly awkward light curve in a sky full of tidier stories. Just like Vulcan, hot Jupiters, and dark matter-rich ghosts, it reminds us that our current models are built on a small collection of examples. When something does not fit, when a planet orbits backward, when a galaxy grows too fast, when a star flickers in ways we have never seen, we are invited once again into that fragile place between certainty and curiosity, where the universe quietly suggests that there is still more to learn. The strange behavior of that distant, flickering star did more than puzzle astronomers. It pulled them together. Telescopes on mountaintops and in orbit turned in unison. Data was poured over with quiet intensity. Models were built and rebuilt. And, threaded through it all, there was a soft strand of imagination. It was a reminder that in science, a mystery is not a dead end. It is an opening, a doorway into questions we did not know how to ask before. Some of those questions lead us away from stars entirely into places where planets drift with no sun at all. In our own solar system, every world belongs to a family. The planets circle the sun in graceful loops, warmed by its light, tugged gently by one another's gravity, wrapped in the faint company of moons, asteroids, and comets. It is easy to think that this is what a planetary system must be. A star in the middle, planets in orbit, everything bound together like children around a fire. But the galaxy is stranger and lonelier than that. There are worlds that do not circle any star, planets set adrift in the dark. Astronomers call them rogue planets. They are almost invisible. Planets do not shine by their own light, and without a nearby star to illuminate them, they vanish into the black. The usual tricks for finding exoplanets do not work. There is no parent star for them to dim, no regular wobble to track, no repeating pattern to betray their presence. Instead, the rare times we glimpse them are usually through indirect, fleeting signs. A momentary bending of starlight, a faint warmth in infrared, a slow, solitary drift against the distant pattern of stars. One of the most powerful tools for this is gravitational microlensing. When a compact object passes in front of a background star, its gravity acts like a tiny lens, magnifying the starlight for a short time. If that lensing event is sharp and brief, and if no star is seen where the lens should be, astronomers suspect a free-floating planet, dark against the dark. These events cannot be predicted. They simply happen. And if we are watching, we catch them. A few such candidates have already appeared. Some seem to be roughly Earth-sized, others closer to giant worlds like Jupiter. In star-forming regions such as the Orion Nebula, faint objects have been spotted wandering without obvious stellar parents, hinting at a whole population of unseen worlds. Icy spheres, rocky globes, swollen gas giants, all moving silently through interstellar night. How do they lose their suns? In one story, a rogue planet begins life just like any other, a seed growing within a disk of gas and dust around a young star. But its system is crowded or unstable. Giant planets jostle each other, their orbits crossing and tugging in complex ways. A close encounter slings one of them outward, giving it enough speed to escape the star's pull entirely. Once free, it does not slow down. It simply keeps going, falling around the galaxy rather than around a single sun. In another story, some rogues may be born directly from collapsing clumps of gas, the same way stars form, but never quite massive enough to ignite nuclear fusion. They would be star-like in origin, planet-like in size, lingering in that gray space between giant planets and tiny failed stars we call brown dwarfs. The line between these categories blurs, and our tidy definitions begin to fray. Whatever their origins, these wandering worlds force us to widen our ideas. A planet no longer has to be a loyal companion. It can be a solitary traveler, part of the galaxy but not of any solar system. Some estimates suggest there could be billions of such objects in the Milky Way, perhaps as many as the stars themselves. Cold, dark, and mostly invisible, they might seem like perfect symbols of emptiness. Yet even here, the universe leaves a small crack open for possibility. A rogue planet can still hold heat inside it, left over from its birth or slowly generated by radioactive elements. If it is large enough, a thick envelope of gas could trap that warmth. Under a blanket of hydrogen, a surface might remain surprisingly mild, even without starlight. Deep below an icy crust, Hidden oceans could be kept liquid by internal heat, much as scientists suspect on some of Jupiter's and Saturn's moons. Life, if it ever arose there, would live not by sunlight, but by the slow, steady warmth rising from within. These are distant speculations for now. Without a star to backlight them, most rogue planets will stay invisible, revealed only in rare moments when they drift in front of more distant suns, or through the faint whisper of their own heat. Future observatories designed for microlensing, like upcoming wide-field space telescopes, may catch more of these events and begin to turn ghostly hints into a census. Even closer to home, there are whispers of hidden worlds on the edge of our own system. In the farthest reaches beyond Neptune, icy bodies follow elongated, tilted paths. Some of these extreme objects seem to cluster in space, as if their orbits have been nudged into similar directions by something heavy and unseen. To explain this, two astronomers suggested the presence of a ninth planet, a cold giant, perhaps 10 times the mass of Earth, looping slowly through the outer darkness, on a path that could take tens of thousands of years to complete a single circuit around the Sunday. This Planet 9, if it exists, would be another child of mathematics, a world inferred from its gravitational fingerprints, not yet seen by any telescope. Computer simulations show that such a planet could herd distant objects into the patterns we observe, even flipping some into nearly perpendicular orbits. The idea is compelling, but the sky has not yet confirmed it. Surveys have searched and found nothing definite. It may be hiding in a slice of sky that has not been mapped deeply enough, or it may be darker and colder than expected, reflecting very little sunlight against the crowded backdrop of the Milky Way. Some scientists remain enthusiastic, pointing to the way Planet 9 neatly accounts for multiple oddities at once. Others are more cautious, noting that the clustering might be an illusion caused by where and how we have looked. Perhaps the combined gravity of many smaller objects could shape the outer solar system without the need for a single giant. Perhaps a passing star long ago disturbed these icy bodies and left their orbits frozen in place. There is even a quiet suggestion from a few corners that the unseen mass could be something exotic, like a tiny primordial black hole left over from the earliest moments after the Big Bang. For now, Planet 9 lives in a kind of limbo, real enough to guide careful searches, not real enough to claim. New observatories, scanning the sky with deep, regular sweeps, may one day pick it out, a faint point crawling slowly against the stars. Or they may not, and the hypothesis will fade, much as Vulcan once did, leaving behind a more refined understanding of both our instruments and our biases. Farther out, in the cold blue realm of Neptune, another mystery orbits in reverse. Most large moons in the solar system travel in the same direction their planets spin, circling near the equatorial plane. It is the natural outcome of growing together from a rotating disk. Triton, Neptune's largest moon, defies this pattern. It moves backwards in a retrograde orbit, circling opposite to Neptune's rotation. Among major moons, this is unique. Triton is not a tiny captured rock. It is larger than Pluto, with enough mass to shape itself into a sphere. Its backward path is a loud hint that it did not form where we find it now. Instead, it was almost certainly captured, seized by Neptune's gravity long ago. But capture in space is not simple. In the vacuum, there is no air to slow a passing body. Without a way to shed energy, an object that swings by a planet will simply arc around and continue on its way. To become bound, something must give. One leading picture begins with a pair, Triton as part of a binary system, two icy bodies orbiting each other like a distant cousin of Pluto and Charon today. As this pair wandered through the outer solar system, they may have strayed too close to Neptune. In that close encounter, the planet's gravity could have torn the partnership apart, flinging one member away while capturing the other. Triton, in this story, is the one that stayed. After such a capture, its orbit would not have been gentle. It would have been stretched and tilted, looping far from Neptune and then swooping close again. Each close pass would raise tides, Neptune pulling on Triton, Triton pulling on Neptune, stretching and squeezing the moon ever so slightly. Over millions of years, that tidal friction would bleed away orbital energy, rounding Triton's path into the nearly circular retrograde orbit it has now, and turning some of that lost motion into heat inside the moon. That quiet heating could explain why Triton, despite living in the deep freeze of the outer solar system, shows signs of surprising activity. When Voyager 2 flew past in the late 1980s, it found a surface that was smooth in many regions, with few impact craters, icy plains, and strange dark streaks. It even saw geysers, plumes of nitrogen gas rising several kilometers above the surface, powered not by sunlight, but by processes within or just beneath the ice. This kind of cryovolcanism, volcano-like behavior, using volatile ices instead of molten rock, is rare, and it hints at a dynamic interior. Triton's arrival likely reshaped Neptune's whole moon system. Compared with Jupiter and Saturn, Neptune has fewer, large, regular moons. Some may have been disturbed or destroyed when Triton was captured, their orbits scrambled, their bodies shattered or swallowed. The remaining small outer moons, with their tilted and elongated paths, may be survivors of that ancient chaos, or fellow captives gathered later. We see echoes of this story in smaller ways around other planets. Mars's tiny moons look like captured asteroids. Jupiter and Saturn host swarms of irregular satellites on odd, looping orbits. But none combine Triton's size, backward motion, and geological vitality. It is as if a dwarf planet from the Kuiper Belt, a world that might once have wandered in the same realm as Pluto, was pulled inward and forced into a new life as a moon. By tracing these crooked paths of Triton, of distant icy bodies, of hypothetical worlds and lonely rogue planets, astronomers slowly piece together a history that is messier and more dramatic than the simple textbook diagrams suggest. Planetary systems, including our own, turn out to be restless, capturing and ejecting, flipping and heating, settling and reshaping over billions of years. One day, a new mission may slip into orbit around Neptune and linger there, watching Triton up close, with eyes far sharper than Voyager 2's brief flyby could offer. Until then, we hold these hints as best we can. A backward moon, an unseen planet, worlds without suns, and the sense that every time the universe behaves strangely, it is inviting us to listen a little more carefully to its story. Scientists are especially drawn to Triton because, beneath its frozen crust, there may be more than ice. If tidal heating has kept its interior warm, pockets of liquid water could linger below the surface, hidden oceans locked away in the dark. And whenever water appears in a story like this, another question quietly follows behind it. If there is an ocean, could anything be living there, kept company only by the slow creak of ice and the distant pull of a blue giant planet? Questions like that echo in other mysteries too, where the clues are not frozen plains or backward orbits, but brief whispers on the radio sky. In the summer of 1977, at a radio observatory in Ohio nicknamed Big Ear, a strip of printer paper rolled out with numbers and letters marching across it. Most of the time, Those characters were the usual low hum of the universe, background noise, earthly interference, familiar static. But one night, a sharp column of unusually strong values appeared at one spot on the page. The astronomer on duty, Jerry Amon, circled that column and, almost without thinking, wrote a single word in red ink. Wow! That one word became the name of the signal. Big Ear was part of the SETI effort, the search for extraterrestrial intelligence. Its task was modest and patient: sweep a patch of sky near the constellation Sagittarius and listen for narrow-band radio signals, the kind that nature rarely produces, but technology might. On August 15th, a signal arrived that seemed to fit the dream. For about 72 seconds, the telescope picked up a strong, clean tone near 1,420 megahertz, the natural emission line of neutral hydrogen, an important marker in cosmic radioastronomy, and a frequency many had long imagined could serve as a kind of universal hailing channel. As the Earth turned and the telescope's view swept past, the signal rose, peaked, and faded exactly as a steady source in space should. It did not flicker in a way that suggested local interference. It did not spread over many frequencies. It was just a single, focused spike, quiet before and quiet after. On paper, it looked almost exactly like the idealized plots in SETI textbooks. And then, nothing. The signal never repeated. Big Ear listened again. Other telescopes joined in over the years. The same patch of sky was checked and rechecked. No second wow ever came. In science, a one-time event is both precious and frustrating. Too real to ignore, too lonely to study easily. Over the decades, explanations have drifted in and out of favor. Some suggested exotic natural sources, pulsars, unusual gas clouds, something in interstellar hydrogen. But none of the known candidates fit the narrow, intense, short-lived shape of the signal at exactly that frequency. Others preferred a more mundane origin, a stray terrestrial transmission bouncing off space debris, a brief military or satellite signal sneaking through, a quirk of the telescope's hardware. One later idea pointed to comets passing through the region, their hydrogen envelopes perhaps emitting near the same frequency. Yet comet emissions are typically faint and broad, not sharp and loud the way the WOW signal appeared. Big Ear used two feed horns that sampled slightly different strips of sky a few minutes apart. A genuine distant source, steady in the sky, should have appeared in both horns in sequence. The WOW signal lit up only one. That detail keeps some astronomers cautious. But the way it aligned with the hydrogen line and the clean shape of the spike make others reluctant to close the file with a simple shrug. So the WOW signal remains in a strange middle ground, neither confirmed as a message nor dismissed as a glitch. Just a neat column of characters on an old printout that refuses to say more. Meanwhile, new SETI efforts, from large ground arrays to projects like Breakthrough Listen, scan vast stretches of the radio spectrum with sensitivities far beyond what Big Ear could manage. So far, nothing has appeared with quite the same combination of clarity and mystery. 40 years later, another odd visitor arrived, not as a radio whisper, but as a small, hard-to-see object cutting through our solar system on an unfamiliar path. In October of 2017, astronomers noticed a faint point of light moving too fast and on too steep a trajectory to be a member of our usual planetary family. Its orbit did not loop around the sun in the way comets and asteroids born here do. Instead, it traced a long, open curve, a hyperbolic path that marked it as an interstellar visitor, the first ever confirmed, an object from another star system passing briefly through ours. It was given a Hawaiian name, Oumuamua, often translated as a messenger from afar, arriving first. From the beginning, Oumuamua resisted easy classification. If it was a comet, it was an unusually quiet one. As it passed near the sun, it showed no obvious fuzzy halo, no tail, no obvious jets of gas that telescopes could see. In reflected light, its brightness rose and fell in a way that suggested it was quite elongated or very flat, spinning and tumbling so that different cross-sections turned toward us. Some models painted it as cigar-shaped, others more like a thin, wide shard. Then researchers noticed something more troubling. After Oumuamua swung around the sun and began heading outward, its trajectory did not match the path gravity alone would dictate. It was accelerating ever so slightly, veering off by a small but measurable amount. That kind of extra push is familiar in comets, where jets of vaporizing ice act like tiny thrusters. But again, no such jets were seen, and no obvious dust cloud glowed in the telescopes. Most scientists lean toward natural explanations anyway. Perhaps Oumuamua was shedding gas in a way that produced little visible dust, or perhaps it was composed of unusual ices, like molecular hydrogen or nitrogen, that would evaporate without leaving a bright trace. Others imagined it as a fragment, chipped off a larger body in some distant system, its strange shape sculpted by long journeys between stars. A smaller group allowed themselves to ask a different question. What if the acceleration came not from hidden jets, but from light itself? If Oumuamua were very thin and broad, they argued, the gentle pressure of sunlight could account for the observed drift, much as wind can move a sail. In that case, it might be some kind of artificial structure, perhaps more like a discarded light sail or a piece of technology than a natural rock. It was, and remains, a minority view, but the mere fact that it was taken seriously at all shows how far Oumuamua strayed from our expectations. The data, however, are limited. By the time its interstellar origin was recognized, it was already leaving. We had only a short window to measure its brightness and motion before it slipped beyond the reach of our best instruments. No spacecraft was near enough to chase it. What we have now is a thin collection of light curves and positional measurements, from which many different stories can be spun. A second interstellar visitor, discovered later and named Borisov, behaved exactly like a normal comet, with a clear tail and familiar activity that only deepened the contrast. One looked like a standard icy wanderer from another star. The other looked like an exception wrapped in question marks. Together, the WOW signal and Oumuamua sit in a quiet corner of our shared imagination. Neither is proof of anything beyond nature's own weirdness, but each flirts with possibilities at the edge of the known. They blend into a larger, older question that hums beneath so much of modern astronomy. If the universe is this large and this old, if stars and planets are so abundant, why do we keep finding only hints and never a clear hello? That question is often gathered under a simple name, the Fermi paradox. Years ago, at a lunch table, the physicist Enrico Fermi is said to have listened to his colleagues talk about the likelihood of intelligent life elsewhere in the galaxy. They discussed the vast number of stars, the potential for habitable worlds, and the time available for civilizations to rise. After a moment of quiet, Fermi asked, "Where is everyone?" It is a deceptively soft question. Our galaxy is more than 10 billion years old. Earth formed about 4.5 billion years ago. Humans, in our current form, have existed for only a thin sliver of that history. If life can arise on other worlds, even rarely, and if some of those life forms can build technology, then many civilizations could have reached maturity millions or billions of years before us. With that much time, even slow ships and self-replicating probes could drift from star to star, gradually spreading through much of the Milky Way. If that is true, then why is the sky so quiet? One answer is that perhaps the path to beings like us is far steeper than we imagine. Life may sprout easily, but complex, intelligent life could be extraordinarily rare. On Earth, simple organisms appeared early, yet it took billions of years for creatures capable of building radios and rockets to appear. Those long, uncertain steps, from chemistry to cells, from cells to multicellular life, from animals to minds, might rarely align. Another answer is more somber. Maybe many civilizations do arise, but most do not last. They might exhaust their resources, ruin their environments, or develop technologies that outstrip their wisdom. The idea of a great filter imagines a dangerous step on the road to becoming a spacefaring species, a hurdle that few survive. If humanity has already passed that hurdle, we might be one of the lucky ones. If the filter still lies ahead, the silence around us could be a kind of warning. There is also the thought that others may be there, but choosing not to speak. In one image, often called the dark forest, each civilization is like a hunter in a night wood. No one knows who else is out there or what their intentions might be, so everyone stays quiet. Broadcasting your existence could invite harm. In that picture, the galaxy is not empty at all, just full of listeners who have agreed, consciously or not, to remain unseen. It may also be that we are simply using the wrong tools. Our searches for signals tend to focus on certain radio frequencies, in certain directions, for limited periods of time. It is like standing on a shore, listening for whispers from across the ocean with a single, narrow-band receiver that you switch on only now and then. If someone is shouting on a different channel, at a different time, or using an entirely different kind of signal, optical flashes, neutrinos, gravitational waves, or technologies we have not yet imagined, we would not hear them. And beyond all of that, there are practical limits. Our instruments are finite, our observing time is scattered, and our own technology is still young. Even if the universe is full of conversations, we may not yet be listening in the right way, or at the right moments. There are, in the end, many quiet, down-to-earth reasons why, so far, our search for company among the stars has come up empty. Space is wide beyond imagining, and the little ears we have pressed against it are still very new. The first radio telescopes capable of catching a whisper from another star were built only around the middle of the 20th century. Dedicated searches for distant signals have been running seriously for just a few decades. We have listened to a thin slice of sky, in narrow bands of frequency, for brief moments in cosmic time. It is a little like dipping a single glass into the ocean at night and trying to decide, from that one scoop, whether the sea holds fish. Even so, the question that Enrico Fermi voiced at that lunch table does not go away. The paradox has weight because it rests on simple counting. There are billions of stars in our galaxy alone. Many of them, almost certainly, have planets. Even if only a small fraction of those planets are Earth-like, and only a small fraction of those ever grow life, and only a small fraction of that life becomes curious and technological, the numbers still suggest that we should not be the only minds looking up. And yet, when we turn our instruments outward, we meet a deep, still quiet. For some people, That quiet feels strangely soothing. It hints that we might be rare, perhaps even unique, a single bright island of thought in a wide, dark sea. For others, the same silence is unsettling. It whispers that something in our picture may be wrong, that the universe is harsher than we understand, or that there is some step in the path from chemistry to culture that almost no world survives. The truth, for now, is that we do not know what this quiet means. It sits in the background of every listening campaign, every survey of strange stars, every argument over whether a signal or an object might be natural or artificial. As our instruments grow more sensitive over the coming decades, we may begin to close the gap between what the mathematics suggests and what the telescopes show. Or the silence may simply deepen, and Fermi's small question will keep echoing softly behind the numbers. There is another, very different mystery written not in missing messages but in the way the universe itself moves. In the late 1990s, two teams of astronomers set out to measure how much the cosmic expansion had slowed since the Big Bang. Gravity should pull everything together. Over billions of years, the combined attraction of stars, galaxies, and dark matter ought to have been gently breaking the outward rush, like a hand resting on a spinning wheel. By looking at distant exploding stars called Type 1, a supernovae, which all reach nearly the same peak brightness, the teams hoped to read that slowing written into the sky. The method was simple in spirit. Because Type 1a supernovae all shine with roughly the same true power, their apparent brightness tells you how far away they are, like a row of identical lanterns placed at different distances. The red shift of their light tells you how fast space was stretching when that light began its journey. Put those pieces together for many supernovae at many distances, and you get a history of the universe's expansion. The surprise was that the lanterns were dimmer than they should have been. They were farther away than expected, as if the universe had done more expanding than gravity alone would allow. Instead of slowing, the expansion was speeding up. Something was not only resisting the pull of gravity, it was overpowering it, pushing galaxies away from each other with increasing strength. It was as though the fabric of space had developed its own kind of pressure, a gentle but persistent anti-gravity that touches everything, everywhere. That something was given a placeholder name: dark energy. Dark, not because it is evil, but because it does not shine or absorb light. Energy, because it behaves as though it is woven into space itself. Today, the best estimates suggest that nearly 70% of the total content of the universe is this invisible influence. The matter we can see, stars, gas, dust, planets, our own bodies, is only a small fraction. Even dark matter, that unseen mass holding galaxies together, is outnumbered by dark energy. The simplest story is that dark energy is just the energy of empty space, a reborn version of Einstein's cosmological constant. In that picture, every cubic centimeter of space carries a tiny, fixed amount of energy. As the universe expands and more space appears, more of this vacuum energy appears with it, and its repulsive effect grows. The details live in equations, but the idea is almost poetic. Emptiness itself has a faint but real urge to push things apart. The trouble is that when physicists try to calculate how much energy the quantum vacuum ought to hold, the numbers explode. Adding up the zero-point energies of all the fields in nature gives a value that is absurdly large, many orders of magnitude higher than what we infer from the actual cosmic acceleration. It is sometimes called the worst prediction in physics, off by a factor of roughly 10 raised to the power of 120. Clearly, something is missing. Some theories suggest there might be a delicate cancellation at work, with huge contributions from different sources, almost exactly balancing, leaving behind just a tiny residue, the dark energy we see. Others imagine that dark energy is not a fixed background at all, but a slowly changing field, nicknamed quintessence, whose strength can grow or fade over time. There are more radical ideas, which say that perhaps there is no extra stuff at all. Instead, maybe gravity itself, as described by general relativity, needs to be modified on the largest scales. To tease these possibilities apart, astronomers map the universe with increasing care. They measure how galaxies cluster, how light is bent by mass, how supernovae behave at different epochs. They are looking for subtle signs that the acceleration is changing, or that structures are growing in ways that do not match a simple cosmological constant. Each new survey is like another long exposure photograph, slowly revealing more detail in the faint pattern of cosmic expansion. Whatever dark energy is, it will shape the future. If the acceleration continues, as it seems to now, distant galaxies will drift beyond the reach of our telescopes. Over unimaginably long times, the night sky would lose its faraway islands, leaving only our local group of galaxies bound together. In some more extreme scenarios, the push could grow so strong that it eventually tears galaxies, stars, and even atoms apart in a big rip. In gentler versions, the universe simply thins and cools, a quiet, ever-expanding dusk. There are even models in which dark energy could change sign, letting gravity win in the end and pulling everything back together. All of those fates hinge on something we can name but do not yet truly understand. Beneath that question lies another, even more delicate one. What does empty mean, really? In classical physics, a perfect vacuum is nothing at all. No particles, no light, no sound. But quantum theory tells a different story. At the smallest scales, fields and particles can never be fully at rest. The uncertainty principle insists on a kind of jitter, a permanent trembling in the fabric of reality. Even when a system is in its lowest possible energy state, there is still a little residual motion, a non-zero flaw called zero-point energy. One of the clearest glimpses of this came from a thought experiment proposed by the physicist Hendrik Casimir and later confirmed in the laboratory. Imagine two uncharged metal plates placed very close together in a vacuum. Quantum theory says that the empty space between the plates is filled with fluctuating electromagnetic modes, but the narrow gap only allows certain wavelengths to exist between the plates, while space outside allows more. That imbalance creates a tiny pressure, nudging the plates toward each other, as if the vacuum itself were gently squeezing them. Experiments have measured this Casimir force. It is small, but it is there, a tangible sign that what we call nothing is restless. In quantum field theory, every field, the electromagnetic field, the Higgs field, and others, carries its own zero-point energy. When we add them all up formally, we get those wildly large values that clash with the mild, almost shy dark energy we infer from the sky. Somewhere between those two pictures, a deeper understanding must be hiding. Because the vacuum seems to harbor energy everywhere, it is tempting to imagine using it, tapping into zero-point fluctuations as a limitless power source. Over the years, many hopeful designs and dramatic claims have appeared at the edges of science. But within the careful framework of known physics, there is no established way to extract network from the quantum vacuum without violating conservation laws. The fluctuations are real, but they are not like a buried fuel we can simply dig up. For now, they are woven into the rules themselves, not available, as a separate resource. Even so, zero-point energy is not just a curiosity. It affects the behavior of atoms, helps shape the forces between particles, and plays a role in technologies like superconductors and quantum devices. It blurs the old line between empty space and something, and it hints that the birthplace of the cosmos might be stranger than a simple explosion in a perfect void. Some speculative models imagine the entire universe emerging from a quantum fluctuation in a larger vacuum, a bubble of space and time budding from an ocean of restless nothing. When you put all of these threads together, the quiet radio sky, the single, unrepeatable wow, the odd messenger from another star system, the missing mass that holds galaxies in place, the invisible pressure that drives them apart, the restless vacuum that refuses to be truly empty, you get a picture that is both unsettling and gently reassuring. Unsettling, because so much of what shapes reality lies beyond direct sight, and because our most trusted theories now carry visible cracks. Reassuring, because at every edge where understanding frays, curiosity steps in. People build new instruments, gather in quiet rooms to puzzle over data, invent ideas bold enough to be wrong, and send them out into the world to be tested. Somewhere in that long, patient work, the universe is slowly telling us more about itself. And as you lie here listening, the galaxies continue their slow dance, the cosmic expansion carries on, and the quantum vacuum hums softly under everything. The silence between the stars is still there, but it is not empty. It is filled with questions, with possibilities, and with the faint, steady glow of a universe that is still unfolding its story, one quiet mystery at a time.